Hello everyone, I'm Yang.
And I am Zhang.
Today we'll be explaining the sieve of Eratosthenes and how we turn it into an algorithm.
The Sieve of Eratosthenes is one of the most famous algorithms for finding prime numbers. It was originally designed by the Greek mathematician Eratosthenes. The goal of this algorithm is to find all prime numbers that are less than or equal to a given number, say n.
Exactly. Prime numbers, just as a refresher, are numbers greater than 1 that are only divisible by 1 and themselves. So if you need to find all the prime numbers up to, let's say, 50, doing it by trial division will be inefficient. This is where the sieve comes in.
Right. The sieve uses a systematic approach to cross out any non-prime numbers, leaving only primes behind. The magic is that it does this so much more efficiently than checking each number individually for primality.
To understand how the sieve works, imagine a list of numbers from 2 up to n, which is your upper limit. Starting with 2, the smallest prime number, you mark all multiples of 2 as non-prime because they are divisible by 2.
Then you move on to the next unmarked number, which will be the next prime, and mark all its multiples as non-prime. You repeat this process until you've marked all multiples of all primes up to n.
Let's break this down with an IB pseudocode explanation. Here's how we can structure the sieve of Eratosthenes algorithm.
The pseudocode begins by generating an array called prime that contains n Boolean values. Initially, all values are marked as true, meaning they're considered prime numbers until proven otherwise.
Exactly. The loop runs from 2 to n, checking if each number is prime. If it is, the multiples of that number are marked as non-prime by setting their corresponding values in the array to false. After designing the sieve in pseudocode, we implemented it in Python version 3.12.4. The process is quite similar, where we generate a list of Boolean values indicating whether each number is prime or not.
First, let's look at how we implemented the sieve in Python. Here's a snippet of our Python code.
In this Python code, the list test array represents whether each number is prime. All values are initialized as true, and then we mark the multiples of each prime starting from 2 as false. However, two versions of code were designed to display the similar output in different ways. In the first version, with each line marked with a number sign in the front, prime numbers are printed out as soon as they are found, whereas the second version append the prime numbers to an empty list and print out the entire list at once, which makes it simpler for plotting the graph later on.
Now let's define the function Pn, which gives us the cumulative count of prime numbers up to n. This will help us visualize how prime numbers accumulate as n increases.
To design this function, we create a list named number of prime, which simply counts how many prime we've found so far on the last part of the code.
And when we plot this, it gives us a nice visualization of the distribution of primes and how their cumulative count increases as n grows. Now, to really put this algorithm into action, we wrote a Python function that plots the prime numbers up to a given value using the matplotlib library.
The prime numbers that we found, as recorded in the list prime numbers, are used as the x-coordinate of the plot, and the number of the prime numbers is used as the y-coordinate.
This code creates a scatter plot of the prime numbers, with the prime numbers on the x-axis and the cumulative count of primes on the y-axis. It also labels each prime number on the plot, making the distribution of primes easy to see.
It's a great way to visualize not only which numbers are prime, but also how the number of primes accumulates as n increases.
So that's all about the sieve of Eratosthenes. It is an efficient and elegant solution to the problem of finding all prime numbers up to a given number.